In our previous lecture, we looked at the response of a linear system to an input that was cosine omega t. And what we found was the output would also be a cosine at this frequency. The difference between the input and the output was one of magnitude and phase. The magnitude, labeled A here, is given as the absolute value of the complex number g of j omega, where g is the transfer function of the system. The phase is labeled phi, where phi is the angle of g of j omega. One way to look at the complex gain g of j omega is to imagine it as a vector in a complex plane. In this case, the vector has length a and has an angle with respect to the real axis of phi. Now we should note that this complex plane is not the same as the complex plane that we refer to as the S-plane. The units in the S-plane are frequency, but the units in this plane are complex gain. What that means is that the units of this plane are the units of y divided by the units of x. So if the output had units of meters and the input had units of volts, the units on the axes in this plane would be meters over volts. We'll now look graphically at the relationship between the input and the output when the input is cosine omega t. And what we want to do is to visualize the difference between the input and output signals. That is, how the difference in amplitude and phase appears. We'll now look at several examples, and in these examples, the transfer function of the system will be labeled h of s. Here's our first example. The input, shown in green, is x equals cosine omega t. It has a unit amplitude. The output, shown in blue and labeled y, has a different magnitude and phase than the input. It's also a cosine wave at the same frequency, but the amplitude of this output is 0.6. Since the input had magnitude 1 and the output has magnitude 0.6, we know at this particular frequency omega that the transfer function relating the input and the output must have the absolute value of h of j omega equal to 0.6. Now I want you to note something about the phase relationship between the input and the output. I want you to note that the output peaks after the input. This is referred to as phase lag because the output's peaking after the input peaks. It's called phase lag because the output appears to lag the input. In this case, the angle phi is less than 0. In the figure on the previous page, the phi that's shown is minus 90 degrees. And you know that since the output peaks when the input is crossing 0. This is called 90 degrees phase lag. So from the plot, we know the magnitude of h of j omega at this frequency is 0.6, and the angle of h of j omega is minus 90 degrees. Now let's look at a second example. The input, x, shown in black, is again cosine omega t, and it has a magnitude of 1. The output, y, shown in blue, has a magnitude of 2. From this, we know that the magnitude of h of j omega at this frequency is 2, because that's the ratio of the amplitude of the output to the amplitude of the input. Now you'll notice that the output, y, peaks before the input. We say that the output leads the input, and refer to this phase relationship as phase lead. In this case, the angle of h of j omega is 90 degrees. You can tell this because the output peaks when the input is crossing 0. Let's now look at a third example. In this case, I'm going to give the transfer function of the system and the input, and we'll determine what the steady state output is. So, the input is x of t equals 2 sine 4t plus 3 sine 15t plus pi over 4. And our system is g of s equals 12 over s plus 7. What would the steady state output be in this case? We know from superposition that the output will be the sum of two sine waves, one at 4 radians per second and the other at 15 radians per second, because these are the frequencies that are present in the input. So we'll write a general form. Y of t equals b1 sine 4t plus phi1 plus b2 sine 15t plus phi2 plus pi over 4. Now we just need to determine what the amplitude for b1 and b2 are, as well as the phases phi1 and phi2. We can determine amplitude b1 simply by multiplying the amplitude of the input at 4 radians per second times the magnitude of the transfer function evaluated at this frequency. The amplitude of the input at 4 radians per second is 2. The magnitude of the transfer function is the absolute value of the complex number g of j4. We can determine b2 in a similar fashion. We'll take the amplitude of the 15 radian per second input and then multiply it by the gain of the system at 15 radians per second, that gain being the absolute value of g evaluated at j15. So to determine the output, we need to find the magnitude and the phase of the transfer function evaluated at the frequency. So let's look at the frequency 4 radians per second. We'll evaluate the transfer function at s equals j times 4. So plugging in j times 4 for s into the transfer function, we find it's 12 divided by j times 4 plus 7. Now, to find the magnitude of that complex number, what we'll do is we'll take the magnitude of the numerator and the magnitude of the denominator, and we'll take the ratio. So we have the magnitude of 12 over the magnitude of j times 4 plus 7. The magnitude of j times 4 plus 7 is going to be the real part squared plus the imaginary part squared, square root. So in this case, it's 4 squared plus 7 squared, square root. So the magnitude of j times 4 plus 7 is 8.0622. So now we can compute the magnitude of g evaluated at j times 4. So that'll be the magnitude of 12, or 12, divided by 8.0622. That comes out to be 1.4884. Now we'll compute the angle of the complex number g evaluated at j times 4. This will be the angle of the numerator minus the angle of the denominator, according to our rules for complex numbers. So it's the angle of the numerator, 12, minus the angle of j times 4 plus 7. The angle of the number 12 is 0 radians, and that's because 12 is on the positive real axis. The angle of j times 4 plus 7 is going to be the inverse tangent of the imaginary part over the real part. So that's the inverse tangent of 4 over 7, which is 0.519 radians. So now we'll put these numbers in to find the angle of g evaluated at j times 4. So that's going to be the angle of 12, which is 0, minus the angle of j times 4 plus 7, which is 0.519. So, doing the subtraction, we find the angle of g at j times 4 is minus 0.519 radians, or that's negative 29.7 degrees. So we're now ready to put the magnitudes and angles that we just found for 4 radians per second into our equation for y of t. We'll have to compute also the values for 15 radians per second. That will be done in exactly the same fashion that we just did for 4 radians per second. We'll just plug in j times 15 into the transfer function for s, and then do the evaluations using our understanding of the magnitude and phase of complex numbers. So we can now calculate the amplitudes of the two frequencies in the output. B1 will come out to be 2.976 and B2 will come out to be 2.1748. We already found the phase angle Phi1 to be negative 0.519 rads. The angle Phi2 will end up being negative 1.134 radians. These numbers are now ready to plug into the equation for y of t. B1 is the magnitude of the sine wave at 4 radians per second in the solution, and B2 is the magnitude of the sine wave at 15 radians per second. Phi1 is the phase of the output at 4 radians per second in comparison to the input's phase. Since the input at 4 radians per second had a phase of 0, the output will have a phase at 4 radians per second of Phi1. Phi2 is the phase between the input and the output at 15 radians per second. The component of the input at 15 radians per second had a phase of pi over 4, so the output at 15 radians per second will have a phase of Phi2 plus pi over 4. So when we insert our calculated values for B1, B2, Phi1, and Phi2, the solution we'll find is at the bottom of the page. Y of t equals 2.976 sine 4t minus 0.519 radians plus 2.1748 sine 15t minus 0.348 radians, where 0.348 is pi over 4 minus 1.134. Let's look again at what we've done in this example. We found the response to an input that was not just a sinusoid, but was a combination of sinusoids at different frequencies. And the way we did this was we found the response to each sinusoid component. And this brings up an important idea, that we can find the steady-state response to complex signals by finding the response to each harmonic component. This is an important idea because, as Fourier showed, we can take all sorts of complex signals and break it up into harmonic components. For example, let's suppose we want to find the response of a linear time invariant system to a periodic square wave input x of t. We'll denote the fundamental period of the square wave as capital T and the fundamental frequency as 2 pi over capital T. The square wave can be decomposed into the sum of sinusoids at frequencies W, 3W, 5W, 7W, and so on. Each of these sine waves needs to have the appropriate amplitude so that when they add together, they compose the square wave. Now, to actually compose the square wave, we would need an infinite number of these sine waves. With a finite number, we achieve just an approximation to the square wave, but with each additional sinusoid added, we'll get closer and closer to the square wave. At the top of the page, you can see the approximate square wave created by the first 7 harmonics. Since we can approximate this input, the square wave, by a summation of sinusoids. That allows us to find the response to this square wave by simply finding the response to each one of these component sinusoids. I hope you can now see the usefulness of this important idea. We can break up an input into the sum of sinusoids and find the response of the input by finding the response of each of the sinusoids and then adding these together.
Like the Laplace transform, the Fourier transform can convert a signal from the time domain to the frequency domain. The main idea behind the Fourier transform is that any signal can be approximated by the linear sum of sines and cosines of the right amplitude and frequency. Here you see a square wave that is approximated by successively adding sine waves of increasing frequency and decreasing amplitude. The Fourier transform and its inverse becomes difficult and slow to compute as more basis functions are needed to approximate a signal. Several algorithms were devised to speed up these calculations. These algorithms are generally referred to as fast Fourier transforms. Let's jump to a simple experiment that illustrates how powerful fast Fourier transforms can be. Here we have a tuning fork with a vibration sensor attached. What we want to do is strike the tuning fork and measure its fundamental frequency with an oscilloscope. However, we have deliberately placed an AC transformer next to our experiment to generate noise. As you will see on the oscilloscope, the vibration sensor is clearly picking up the 60 Hz AC frequency from the transformer. When the tuning fork is tapped, the vibration signal associated with the tuning fork is masked by the AC noise. Most modern oscilloscopes have an FFT function built in. The oscilloscope now shows a plot of all the signals present on its input as frequency versus voltage. You can clearly see the 60 Hz signal on the left of the screen. As the fork is struck again, you see another signal rise out of the noise. The frequency of the signal is 340 Hz. The fundamental frequency is stamped on the side of the tuning fork. It is almost identical to the frequency from the oscilloscope. Most math softwares like Matlab and even Excel have FFT functions built in. Here is an example of an FFT in Matlab. We sampled the voltage output from the vibration sensor attached to the tuning fork and imported the data into Matlab. As you can see on the top of the graph, the signal is identical to that of the graph shown on the oscilloscope. After performing FFT on the data, the result is plotted on a frequency versus power graph. From the bottom graph shown, the left peak is the 60 Hz frequency from the AC transformer, and the right peak is the 340 Hz generated by the tuning fork. What are some other uses of FFT? In a previous lecture, Professor Knospe showed a car body undergoing a vibration test. He mentioned that in order to offer a better ride to the passengers, only the lower frequency vibrations were allowed to pass to the car frame and higher frequencies are attenuated by the suspension. But how could you possibly measure in real time what frequencies are being passed to the passenger car and which ones are absorbed by the suspension? Suppose you record someone dialing a number on a touch-tone phone. The DTMF, or dual tone multi-frequency signal, is a set of two frequencies combined to create a single tone. Using FFT, you can separate the two frequencies and determine what number is being dialed. Here is a phone number being dialed on a touch-tone phone. The question is it Professor Knospe's personal cell phone number or the number to the local field office for the FBI?